Hello, everyone. My name is Ricardo, and I would like to talk about growing a workflow language with GNU Geeks. Who has not heard of GNU Geeks before? Oh, so you may want to stay in this room because there's going to be yet another talk about GNU Geeks. It goes a bit more into depth. I'll explain the rough idea, okay? So you shouldn't get lost. This is not the story of a product, but it's the story of an idea. It is not my idea. It is an old idea. An idea as old as organized computing, maybe. And it begins like this. Once upon a time, there was a little process. It produced output as if to prove its existence. Then it disappeared into the void from whence it came. Now prepare for the tragedy. In its brief life, it never met any other processes. This all changed when, at long last, the pipe arrived. The concept of a pipeline was born. This is the pipe. This is one process. This is another process. And they meet in the middle. This one produces something. This one consumes what the previous process produced. This was a beautiful concept because the little process was no longer alone. But like every beautiful thing, it turned into something, into a monstrosity. Pipelines grew ever larger, as did the compute requirements. No longer was it sufficient to have a process and another process that communicate with one another. When researchers of the life sciences understood the concept of computing and the value it provides for biology, for example, they tried to scale this very simple concept, this very simple idea, to the genome scale, right? Terabytes of data, lots and lots of processes that have to run and compute lots and lots of data to produce a final answer, maybe 42. The process is never as simple as that. It's not just align the genome and then pass this to some process that analyzes it. No, we need a new spin on this idea of processes. High-performance computing. This is really just lots of low-performance computing, but connected. Now, an obvious problem with this is that these are different machines, right? You can't just use a pipe for that. You still have processes, but how do you connect them? A pipeline is just a process connected with another process, maybe connected to yet another process. But the concept of a workflow is an expansion of the idea of a pipeline. Rather than having a linear flow of data that goes in from the left and comes out at the right, you have a graph where information can disperse and seep through. And at the end, you filter out something that you're interested in. But like any simplified story, like this one too is made up of lies. I said that this is a process, right? This is true. This is a process. But much more important than the process itself is the much larger environment in which it runs. We don't speak computer languages. We interact with computers through a very simple string-based language, right? We have names of processes, and the computer invokes them for us. We can't actually control the process. We just give the computer a name, and depending on the environment, it generates the process for us. So the environment is really crucial in what effects there will be when we invoke a command. But the environment is not just this gray blob, this looming shadow in the background. If we zoom a little closer into that, it consists of things. It consists of files, packages, applications. This is just a very simple real-world environment. It's a very simple environment. It's just one for creating an environment for GCC, for example. This is just one compiler. In real workflows, we have much larger environments that we can't possibly comprehend by just looking at it. Even if you spend an hour looking at this, we probably won't understand what this does, how it behaves, what implication this environment has on the process running inside of an environment like this. Can containers help? No. Okay, let's move on. Containers. Containers are the idea that you can wrap up an environment, the binary state of an environment, instantiated at a later point, on a different machine maybe, and that way you can be sure that the process running inside an environment has a well-known environment to operate in. But containers are weird. You know, we use the term containers, but it's really an application bundle, right? It's a lot of state thrown in together. And when you think of it that way, they are very much like a smoothie, right? It's the result of something. It is an output of following a recipe that you may no longer have access to. Containers lack transparency. You don't really know what is inside once you have the result. Now some of you might say, oh, well, but what about things like Docker files, right? Isn't this a recipe? It is a time-based recipe. It depends on where you run it and when you run it. Generating a Docker application bundle, this binary blob, depends on the state of the world, right? That was used as an input to the procedure generating the state. So containers are not actually a solution. They are not an input. They are outputs. So what can we do about this? So I'll be honest. This is a thinly veiled advertisement for GNU Geeks. GNU Geeks is often called a package manager. But when you hear package manager, maybe you think of npm, God forbid, or you think of apt for Debian, right? Or you think of PyPy. Or there are so many package managers. Package manager does not begin to describe what Geeks does. Yes, it allows you to manage packages. It builds packages in a reproducible fashion by design. Reproducible means that you build a package today according to a recipe, and it results in a certain kind of output in a certain binary state, and you do the same thing tomorrow or a week from now with the same recipe, you get the same output. You get the same binary state. So same inputs, same output. The idea behind that is called functional package management, which was pioneered by Nix. But it's more than just packages, right? Multiple packages together form an environment. Geeks allows you to manage environments, create isolated environments, create impure environments that are like a mix of the state you have on your system and the one that you want to have. But it also allows you to put those environments into isolated containers. There's contexts of execution where certain aspects of the environment are eliminated. For example, user names. You can create a user namespace in which the process running inside context within which the user running the process is root, for example. The process thinks, oh, I'm running as root. But really, looking at it from the outside, there is no such thing as root. You can also virtualize the file system. Right? You can say these files don't exist, only those files exist. Containers are a very powerful idea that is orthogonal to the idea of bundling up binary state and shipping this around. More than that, though, Geeks can allow you, Geeks enables you to build complete systems. By system, I mean an operating system that runs on, for example, this laptop here, or on an HPC cluster, or a virtual machine. Because to Geeks, this is all the same. It is all about building things, recipes, in a reproducible fashion. So that at the end, we end up with exactly the kind of state that we declared at the beginning. So in short, what Geeks provides is reproducible deployment in a very generic way. Now, this is actually about the workflow, the Geeks workflow language, right? You can think of it as an extension to Geeks itself. So this is not to scale. The workflow language is actually even smaller. Right? So Geeks is this is the minimalist language track, right? So this is the way it's supposed to be. So there's Geeks, and out of Geeks we grow extra features that describe, that provide enough features to allow us to express workflows. Now back to the original idea. We had processes and we had the pipes. The pipes are really just means of composition. So we have means of abstraction to describe what a process is, maybe describe its complexity, its resource requirements, or simply its name, so that we have control over it. And the workflow is just the composition of many processes. And this is really all there is to it. Brace yourself. If you're not a schema, this may look really, really ugly. But bear with me. In 2 more slides, these parentheses will disappear. So this is very, very simple, right? This is a process that has a name. So we can refer to it and we can invoke it. It has package inputs. This one uses the GNU Hello package, whose purpose is to greet you. When you execute it, it says hello world. And the process has a procedure. This is the way how it is supposed to be executed. Right? This is some special syntax. You don't need to know that. This just says, it's like syntactic sugar that allows us to run a little shell snippet where we execute hello. Right? Process is very, very simple. The package inputs field is where the magic lies. So this is where it connects to Geeks. When this is invoked, Geeks will generate the environment that provides hello and nothing but hello. So that within this context, we have a specific version, a specific variant of the hello package that we can execute and get the greeting that we want. Because maybe in hello 3.0, the greeting may change to hello Jupiter. Who knows, right? Workflows. As I said, workflows are just the means of combining processes. This workflow has a name, flow. This is a common workflow name. And it consists of processes that are connected in a graph, right? So there's a process A that does things an A process would do. And A depends on the B and C processes, the outputs of B and C. Maybe B generates something first that A consumes. And it also depends on C. Now, B itself depends on the execution of D. Right? So this is a very, very simple description of how these processes are supposed to be plugged in. Now, for those who don't like S expressions, just a sec. This is a different way of expressing the exact same thing. Right? This is what schemas see when they, or what Lispers see when they look at S expressions. They don't see the parentheses, they see the structure. Okay? So you can simply write that structure if you feel like it. This is called WISP, and there's going to be a talk later today about this language extension, which is a minimalist language in itself. There was a question.
When you read it, you read D depends on D. The data flows from B to D or from D to D?
This is actually a future extension that is currently in works. There are different ways of expressing the same thing, right? So the question was about if this is a data flow expression, that data flows from A to B and C, or if it goes the other way around, right? This depends on. A depends on whatever B and C provide. You can express it the other way around, flipping the arrow and saying data that is pushed into B and C is later consumed, is later pushed through to A.
So it's just the express dependency, it's not communication flow.
It's not communication flow, yeah.
One more question, sir.
Yeah.
Can you express everything you can with this language as in S4?
Oh, with Wisp?
Yes.
Can you express everything with Wisp that you can express in S expression? Yes. You can also try to let it figure things out for you. If you don't really want to specify how data flows from one process to the other, simply by declaring inputs of A and outputs of A, and inputs of B and outputs of B, you can simply line those up and automatically connect this. For some workflows, this is the easier way of describing things. Sometimes you don't want to know the details. You want the system to just figure it out for you. All right, this is an extension to GNU Geeks, so it provides naturally a command, a subcommand, so Geeks workflow, which allows you to run workflows or to inspect workflows, to generate a nice representation of the workflow. It is not a separate tool, right? It came growing, budding out of Geeks, if you will. The features that it gains by being embedded in Geeks are plenty. I didn't have to write any of this. In fact, I didn't write most of it anyway. This is a project I took over. But reproducible packages, for example, is one thing that Geeks provides. The workflow language doesn't have to do anything to gain access to thousands of bit reproducible packages. This is beautiful, right? It has access to a special form of expression, which is called a G expression, a Geeks expression, if you will, that allows you to more conveniently access packages from within what looks like an S expression. So that's a special case. If you know about Geeks, this will make sense to you. Container context, as I said, Geeks provides the ability to set up containers, mount file systems in the right locations. The workflow language gains this for free. You don't have to do anything to make it happen. Same with virtual machines, right? Geeks can build systems. The workflow language has this feature at its disposal. Workflow bundles. Having a workflow description locally may not be the most convenient way for other people to run that workflow. Right? Maybe they don't have Geeks for whatever reason. So Geeks provides a feature with which you can package up the whole environment and create those infamous bundles, these binary blob bundles. We can bundle up workflows just like that. And data caching, this is actually not directly a feature that Geeks provides, but Geeks provides caching, if you will, for package builds, because they are built reproducibly. So we don't have to rebuild packages when none of the inputs have changed. The same goes for data, right? If you have data files that haven't changed, why would you have to regenerate the output? Right? If you already have the output file, if none of the inputs have changed, there's no point in rerunning this. So you gain caching. Being embedded in Scheme, a language known for being a good language for writing languages, allows us to simply add syntactic sugar, right? We gain a big chunk of syntactic sugar, which is probably not good for you, through Wisp. But we can also embed other processes or syntax for expressing graphs and whatnot. It also allows you to execute these workflows on HPC systems, right? There's grid engine execution stuff. You just have to specify that you want to run this workflow on an HPC cluster. And since the time is up, right. I just leave this here for you. You can look this up later. The slides go up somewhere. Yeah. We've talked about all of this. So this is it. We have grown a workflow language, and we will see if this was a good idea. Mm-hmm. Thank you.
Next speaker set up.
Yes, please.
This language was mainly developed with bioinformatics in mind, maybe. Has there already been a bioinformatics experiment that used this language?
The question is, the origin of this workflow language is within the context of bioinformatics. Are there any workflows that use this language? Yes, there are. It actually does work on real-world workflows within the context of bioinformatics, but this doesn't have to be limited to bioinformatics. Bioinformatics is just one weird case, one special case of scientific computing in general. Yeah.
How is GIGS related to NICS? Because I've heard about the GIGS for the first time.
Mm-hmm.
Yes, the name I heard it before, and some of those looks very similar to NICS.
What is the relationship between GIGS and NICS? Right? NICS was first. GIGS was second. GIGS is an implementation of the same ideas that were pioneered in NICS. With the implementation of GIGS made a couple of different design decisions, and there are different approaches to exactly how this core idea is implemented. Both projects face the same kind of challenges, so there's a lot of collaboration between them. In fact, we just had a short conference, a 2-day conference before FOSDEM, where NICS folks were present, because the problem space that we both occupy is virtually the same. All right, thanks.